This video has been put together to help new users of Mtex get up and running. Everything from downloading Mtex and installing it on your computer, through importing of eBSD data, and finally to using simple scripts to conduct some simple analysis on your eBSD data. So firstly, what you will need is a valid version of MATLAB with a valid license. This can be obtained by students from the University of Manchester from the IT services. Then you will need Global Protect, which is the University VPN. You will need it downloaded and installed on your computer, and then you will need to be connected to the university network in order to access the MATLAB license. Once you have this sorted, you will need a version of Mtex. You can get that from the Mtex Toolbox website here, and at the moment 5.3 is the most recent version. You can obtain any of the previous versions, but it would be advised to get the most recent non-beta version. So you will need to download that file and unzip it, and then what you can also get is the lightform Mtex folder. Now this is a repository of scripts that we've put together that you can use to do some simple texture analysis. So once you have downloaded and unzipped Mtex, you want to take the folder and put it into a known location. I would recommend putting that into your documents folder, as MATLAB already creates a MATLAB folder in your documents. Place the lightform Mtex folder in the same location so that you can easily access the two folders. Then you want to go to the current folder tab within your MATLAB and navigate to the MATLAB folder where you placed the Mtex folder and the lightform Mtex folder. Then you want to go ahead and right click on each of these folders, go to add to path, and then selected folders and subfolders, and this will allow MATLAB to access any files contained in these folders. The next thing you should do is go to the command window and type in the command startup Mtex and hit enter. So this will initialize Mtex. Just to say at this point that you may come up have some errors thrown up. One issue can be that the files have not been compiled properly. So you can get around this by downloading Xcode, installing Xcode on your computer, and then MATLAB will recompile the Mtex files automatically using Xcode. Another issue that I've had so far is that with the new version, the new OS X version Catalina, Apple have decided to make their security a lot tighter and will not allow you to use anything written by a non-verified Apple developer. So if you have this problem come up, get in touch with myself or Chris Daniel, and we should be able to help you get around that issue. Now that Mtex has been initialized, we want to go ahead and import some eBSD data. We can do that using the import GUI. First of all, you need to click on the import eBSD data which came up on initialization, and that will bring up the import wizard. Next, click on the plus sign in the corner, and this will allow you to search your computer to find your eBSD data file. Now, inside the lightform Mtex folder, we've included a sample dataset that the scripts included in the lightform folder will work on. You can import various data formats, and if you want to know if your format is supported by Mtex, you can go ahead to the Mtex documentation webpage, and it will show you all of the formats that are supported. But once we get to this point, we just need to follow the prompts to describe our data. So the first step is describing the crystal symmetry. Mtex should actually read each of these phases adequately from the GUI. So the first phase is always your non-index points. Click next and it will come up with your first phase that was actually indexed, and in this case it is titanium cubic. And here Mtex will describe everything about the phase that it needs to know. So for example, the Lao group, the axis length and the axis angles. And the second phase included in this dataset is titanium hex. If you do have a phase which is not recognized by Mtex, you can actually go ahead and find the CIF file online and import it yourself. So the next step is describing your specimen reference frame. First thing Mtex asks you to do is if you want to apply a rotation. At this point, I would recommend just ticking the final box and not applying a rotation, because we can do this later in the script. And then the next thing you want to do is confirm what the plotting convention is. And as far as I'm aware, in the Aztec system that we use on the test scan, for example, X is east and Y is north. It will come up with a summary and we just click finish. And now MATLAB or Mtex has created this import script which describes your data sufficiently, the crystal symmetries, the plotting convention, where the data file is located, and then it will, when we click run, it will import this data and save it as a variable called EBSD. So now that the import script has been created, you can go ahead and save that and run it in order to import your EBSD data. However, I am not going to do that. I'm going to close this, as here is one that I made earlier. So what we can do is run each of these cells one by one. On a Mac, you do that by pressing Command, Shift and Enter. So run the first cell and you'll see that the variable CS, which contains the crystal symmetries, has appeared in the workspace. And we've also set the plotting convention. Then we specify the file names and import the data. So now we can go ahead and start manipulating our data. So the first thing I'm going to do is apply a rotation to the data. So I know that the Euler angle rotation I need to apply is 90, 0, 0. And at the same time, I'm going to define what the X, Y, and Z vectors are. So X will be RD, Y will be TD, and Z will be ND. And then later on in the script, I can use these definitions for if I want to plot an IPF map from a certain direction, then I just need to type in RD, and it will give me the IPF colouring of that direction. So I'll run that cell. And then the next thing to do is to plot a simple IPF map. Now, we've gone ahead and taken the code to plot an IPF map and turned it into a function. You can find the function in the lightform Mtex folder. So the first one I'm going to do is the simple IPF map. Now, here's the syntax which creates the IPF map. But by making it into a function, all you have to do is pass the following arguments. So, run the command IPF map, pass the first argument, which is the EBSD dataset that we imported into the workspace, specify which phase we want to plot. So we'll plot the hexagonal phase, and we want to see it from the rolling direction. So if we run that cell, then we get the EBSD data plotted of the hexagonal phase in the rolling direction. So if I now want to see the cubic data, I can change the specimen symmetry to titanium cubic and run that line. And now we have both the hexagonal and the cubic data plotted. So we've plotted our initial EBSD data sets, but the problem with this is that it still seems a little bit messy, and we can do some reasonable cleaning to the data set. So previously we plotted just the EBSD data points, but what we can do is use this command called calc_grains. Now what calc_grains does is it takes an EBSD data set and it produces a list of grains, and those grains are defined by a misorientation threshold that you pass through to the function. And what it does is it takes that reasonable misorientation threshold and it will draw a grain boundary between 2 points that have this sufficient misorientation between them. So in order to run the command, we need to pass it the EBSD dataset and the angle which we consist to be a grain boundary. And in the workspace, a new variable will appear called grains. Now, grains is, as I said, a list of grains, which each grain has a unique ID. Each grain has its own grain size. But then there's all the other information about the boundary segments. But importantly, what we're going to use at the moment is this mean orientation. So instead of plotting all of the individual EBSD data points and their individual orientations, calc_grains takes the mean orientation of a grain and will plot that as a single color to determine the grain orientation. So we can use this function that we've created called IPFGrainsMap. We pass it the list of grains that we just calculated. We give it the phase that we want to calculate, that we want to use, and again we give it the direction. So if we run that cell, then we now have the same EBSD data set, but now it's plotted as the individual grains, which now have one single color for the grain, which represents the mean orientation of that grain. But we still have a problem here, and that's that the data is still quite noisy, and that comes from all these small EBSD points that with the threshold that we gave it still constitute a grain, but actually just come from noise from acquiring the data. So what we can do there is clean the EBSD dataset by removing those smaller points. So we use this next command called clean_grains, where we pass it the EBSD dataset, we pass it the list of grains, and we determine a threshold, a number of pixels that constitutes a small grain, and it will remove any grains that only have that number of pixels. So once we've run that command, what it's done is it's removed those pixels that constitute a small grain from the EBSD dataset. So it's the original EBSD dataset which has been changed, which means we need to go ahead and recalculate that list of grains again, but now from the new EBSD dataset, the cleaned EBSD dataset. And once we've now calculated that list of grains, this will have changed, and we can go ahead and plot the IPF maps of the list of grains. Sorry, let's make that cubic. And now we have a cleaner version of the previous IPF maps. However, we still have a slight problem here. Firstly, we still have some smaller grains, which we probably could have done a slight removed grains of a slightly larger size. But also, the grain boundaries have this strange stepped effect, and this comes from the fact that the pixels themselves are square, and so inherently a grain boundary will come up with this square stepped effect. So in order to get rid of this, we can use another command called smooth, where we take the grains dataset, we pass that as the first argument through the command smooth, and we set a level of smoothing. So at this point, let's use 3. We run the command, and now we can run the IPF plot command again on that newly smoothed grains dataset. And now you can see that the grain boundaries are more realistic. So up to now, we have imported some eBSD data, applied a rotation to it, and we've plotted that data as IPF maps. But then we've also used the calc grains command to kind of clean the data and then smooth the boundaries to give us some nice looking eBSD maps. So now we're going to move on to plotting a pole figure, which is very simple. First thing I want to point out is the plotting convention. So previously we had the plotting convention set to x is east, but this would give us a problem with our pole figure, as it would put RD to east, and that's not the normal plotting convention. And this, if you don't get this right, if you don't set this up, it can cause some confusion with your pole figures and get you into a right mess. So first of all, we will set the plotting convention so that x is north and z directions into the plane, which will put y to east. So RD will be north and TD will be east, and that actually just rotates these spatial coordinates. The next thing we're going to do is run this line of code for the pole figure. So this can be obtained from the pole figure folder in the lightform Mtex folder. If we pull it up here, then all the code you need is just there. You just need to copy and paste it into your script. So the first line of code will create a new figure. Then the next line will take the orientations, which are saved in the eBSD data set, and we're just looking at the titanium cubic orientation data, and it will calculate the ODF from that, and then we will plot just the 001, the 110, and the 111 pole figures. The next line will actually calculate and plot the ODF, and we can specify that we want it contoured. We'll start the contouring at 0 to 10 in steps of 1, and we will give it the color range to the color bar going from 0 to 10. And then we can also specify things like the location of the color bar and give it a title, for example. So if we run that cell, then we get a pole figure that looks like this. Now there's a few issues I have with this pole figure. Firstly, we've got this strange effect going on in the background, and then it seems like we have too many of these contour lines. So we can go into the code here, and we can say, let's start our contouring at 1 rather than 0 to get rid of that strange effect in the background. Let's go up in steps of 2, so we've got less contouring, and let's go up to 14 because that was the maximum ODF, and then we'll also put our color bar up to 14. And if we run that again, then it will recalculate the ODF. And now we have a much nicer looking pole figure. So this is where Mtex comes into its own, where you can really take control of this and make nice looking figures. Something to note here is that we have X and Y rather than RD and TD, and this is something which you can change, but it does involve going into the settings a little bit more. But apart from that, that's a nice looking pole figure. So the final thing we're going to do with this basic import script is calculate and plot an ODF. Now this, again, piece of code can be found in the lightform Mtex folder, and all you need to do is copy and paste it. So Mtex has this automatic function which calculates what the best half width is for your data, and then all we have to do is use this line here. So again, we create a new figure. We're taking the orientations from the cubic phase of the EBSD data, and we are using the half width that we calculated previously. We specify the specimen symmetry as orthorhombic, and then we use this calc density command to calculate the actual ODF. And then finally, we use the plot command to plot the ODF. We're choosing the phi2 is 45-degree section, and again we're going to contour it and give it a color range. So if we run that command, then Mtex will plot our ODF, which to me looks like quite a nice ODF. The min and max are covering part of the ODF at the moment, and we do have a way of moving this around. It does mean you have to get slightly interactive with Mtex, but this will all be included in the lightform folder. Now I want to show you a script which was written to help people visualize crystal orientations in 3D space. So with this script, you can take an orientation defined by either Miller indices or by Euler angles. You can input it into the script, and then you can plot the orientation as a crystal shape in the specimen coordinate system, but also within a pole figure. So quickly running through it, we define the plotting convention, define which crystal symmetry we want to use, so titanium cubic and titanium hex, and then this will create the crystal shape, and you can do that for any crystal shape you like. So we'll define the pole figure that we want to plot, and then if we just move down to this line here, then we'll define an orientation by Miller indices. So I'm defining the 112, 110 orientation of the cubic phase. Define that orientation, and then if we run the next cell, Mtex will give us the cubic crystal, and it will give the crystal as the orientation that we define by Miller indices. So we can see that we have the 111 in TD and the 110 in RD, and that's maybe something that wouldn't be obvious to you at first. But we can also run the next line here, and we can plot that same orientation by Miller indices but on a pole figure. So now we can see we have the 110 in the X direction and the 111 in the Y direction, which is something that we possibly wouldn't have been intuitive to us, because the Miller indices did not define what was plotted in the Y direction. Finally, if you do have any problems with Mtex, then you can go ahead to the Mtex documentation page. Here you can find tutorials on how to use different aspects of Mtex like EBSD or the grains list. You can also go to the functions reference page, which explains all of the syntax and how to use each of the functions.